Okay, so today what we're going to do is, now that we have this concept of a manifold, okay, and a manifold is more than just a topological space. Now it's a topological space which is locally homeomorphic to Rn, which means that there are open sets that you can cover this topological space with, which are locally homeomorphic to open sets in Rn. And this smooth mapping and also, sorry, the mappings between these open sets in M in regions where they overlap, okay, that mapping, we've defined a notion of differentiability. Okay, sorry, not differentiability, sorry, we've defined a notion of smoothness. Okay, and so now this notion of smoothness basically allows us to transition from one coordinate chart to another coordinate chart in their overlap region. Okay, so we can describe dynamics on the manifold using the coordinates, okay, using these charts, but the manifold itself, or the topological space itself, has a notion of smoothness just associated with it. Okay, and it doesn't matter which chart you're going to use henceforth. Okay, so that's what we're going to see. And also, now we will be able to develop notions of calculus, okay, on manifolds. Okay, so that's what we're going to focus on today, is how to do calculus on manifolds. This notion of smoothness is going to help us do calculus on manifolds. So just to recap this picture, okay, so we imagined a manifold M to be covered by various charts. Okay, so these charts were pairs of UI, which is an open set in M, and phi I, which is a map from this set UI, which is a continuous map from the set UI to some subset, open subset of Rn. Okay, and so again, remember, open subsets are in the context of the topological definition of what an open subset is. Okay, so in the case of Rn, that means open subsets are open balls or unions of open balls in Rn. Okay, and so now we imagine that M is covered by a collection of such UIs and phi i's, and that gives us what is called an atlas, okay, on the manifold M. And now what we're going to do is, you imagine that there are, let's say, there's some region of overlap between these two patches, okay, some U1 and U2. And so in the U1 coordinate system, okay, in any point in this U1 region, can be assigned coordinates, and we label those coordinates as x. Okay, so x by x, we really mean that we will have the components x1 through xn, okay, for an n-dimensional manifold. And for similarly, let's say in this coordinate system, any point in this region of U2 will be labeled by a coordinate y. Okay, and there's maps that take you from the points on the manifold, which are an abstraction. The points exist independent of the coordinates that you assign to them. If I want to go from the point to a coordinate, okay, and this is a particular coordinate choice, I use this function phi1. And similarly, here I can use the function phi2 if the point P belongs to this open subset. If I'm in the intersection region, okay, this intersection region in coordinates, let's say, maps to some point in this white region and this white region over here. And now what I can do is I can define a change of coordinates from the coordinate choices y to the coordinate choice x. Okay, and the smoothness of the manifold ensures that that coordinate transformation is infinitely, it's a smooth coordinate transformation. So in other words, if I take the functions x of y, okay, where by x of y, what I mean is x1 as a function of y1 through yn, x2 as a function of y1 through yn, and on these functions, we know how to define differentiation. These functions are infinitely differentiable. Okay, that's what we mean by smoothness. So basically, I can make coordinate transformations in regions where two patches overlap, okay, and those transformations are infinitely differentiable, or they're smooth. Okay, so once we equip our topological spaces with this smooth atlas of maps, okay, so this covering, so now we have coverings which cover the entire space and where the transitions are smooth. Now we are ready to do calculus, okay, on manifolds. Okay, now that you have this kind of smooth structure on top of this topological space, now you can do calculus, because calculus requires calculating derivatives, and some notion of smoothness is required in order for the derivatives to exist. Okay. The important point is that the calculus that we develop is actually independent of the coordinate system that we choose on the manifold. Okay, and this is something very important to keep in mind, is that it doesn't matter whether we use one particular coordinate system or another. For example, if I have another patch which is, let's say, overlapping with this patch, okay, then in this region it doesn't matter whether we use the coordinates of the u1 or the u2. Okay, either way you'll be able to do calculus. Okay, and there's a dictionary which translates from one coordinate system to another. Okay, and that dictionary is smooth. So so basically this notion of calculus that we'll develop is independent of the coordinate system. However, we will often express things in a particular coordinate in a particular coordinate system. Okay, so we'll see exactly what are the kind of things that we want to calculate, what kind of derivatives we want to calculate, and so on, and how we express them in one coordinate system versus another coordinate system, but how their existence is actually independent of the coordinate systems themselves. Okay. Okay. So now let's talk about one notion of differentiability. Okay, and we'll talk about the idea of differentiable maps between manifolds. Okay, so we already had defined this idea of continuous maps between topological spaces. Okay, continuous maps or homeomorphisms between topological spaces. So now we'll define a similar notion which extends this idea of continuity to differentiability. Okay, now that we have this notion of smoothness on a manifold. So if we take an m-dimensional manifold M, okay, capital M, and an n-dimensional manifold capital N. Okay, now imagine that capital M is covered by an atlas where the charts in this atlas are denoted by u's and phi's. Okay, so u is the open subset in M, and phi is the map from that open subset to Rm, okay, because this is an m-dimensional manifold. Similarly, on N, you imagine that there is an atlas with charts V, and psi, where V is an open subset in N, and psi takes you from a point in this open subset to a point in an open subset of Rn. Okay, so this point is denoted as phi of p. Okay, so if I take a point P here, there's a function phi which takes me to its coordinate, which is phi of p. Now what we can do is we can define the notion of a function which takes us from points on one manifold to points on another manifold. Okay, so we have this notion of a function. Okay, we've seen this before when we talk about topological spaces, right? We've defined functions from one topological space to another. The new thing will be that we'll define a notion of differentiability of this function. Okay, and if in some sense, if this function is infinitely differentiable, then we will say that this is a smooth function from M to N. Okay, so we have to define a notion of differentiability. Now, the obvious problem with trying to define differentiability in the usual way is that the manifold is an abstract space. The manifold is not Rm. Okay, it's locally homeomorphic to Rm, but it's not Rm. Okay, similarly in N, the manifold N is not Rn. Okay, it is some other manifold which is locally homeomorphic to Rn. So this function f is not a function from Rm to Rn, but rather it is a function from, okay, it's not a function from Rm to Rn, rather it is a function from M to N. Okay, takes me from M to N. So we need to have some notion of differentiability which extends to arbitrary manifolds. Okay. However, once again, the fact that we've developed calculus, okay, on Rm and Rn will help us define a notion of differentiability, okay, of this kind of function which takes us between arbitrary manifolds. Okay, and again, since this space M is locally homeomorphic to Rm, okay, we will be able to at least locally define, okay, a function, an equivalent function from the coordinate representation of these points to the coordinate representation of these points, okay, which lie here in Rm. Okay, so this map exists, okay, and the way to think of this map is I take a point with coordinates phi p, I reverse that, so I go back to the point, P. Then I follow F. Okay, so I first reverse, so I go phi inverse. Then I follow F, which takes me to a point in N, which we denote as F of P. Okay, so we follow F. Then we follow psi to find the coordinates of that point F of P. Okay, so that's psi of F of P. So we follow psi. So this is the combination of functions that we use, or maps that we use. And these maps now provide us with a single function which takes us from Rm to Rn. Okay, and on such functions we know how to define differentiability. On maps from m-dimensional space to n-dimensional real numbers, okay, we know how to define the notion of differentiability. So the notion of differentiability of this is assured. Okay, now now we need to ensure that this notion of differentiability can be ported to the entire manifold, because this is only valid in a coordinate patch. Okay, and the notion of differentiability will be you will be able to cover the entire manifold because of the smoothness, okay, of these charts. So even if I move from one coordinate patch to another, I will change coordinates, okay, but I will switch to another coordinate system over here, okay, when I move from this patch P and I go to some other point P prime over here. And then, so even though the way we're defining this is using the local coordinates, okay, since the coordinates are smooth across the entire manifold M, okay, we will be able to define a notion of differentiability which works over the entire manifold M, not just in one coordinate patch. Okay, that is the basic idea of how we will define differentiability. And once we define that notion of differentiability, then independent of the existence of these coordinate patches, we can talk about this F as being a differentiable map from the manifold M to the manifold N. Okay, I'll just pause here for questions, but I'm going to expand on these details now. So any questions about what we just discussed? Is the notation clear, or is the notation getting confusing? I mean, you can just say your individual points of view. It doesn't have to be everyone's point of view. Okay, fine. So I'll move on. Okay, so now let's be clear. So F is a map from M to N. Okay, this map between the manifolds is independent of the coordinates. However, I can choose to talk about this map in a particular coordinate representation, which means I'm now restricting myself to a particular coordinate patch. Okay, so let's say this patch here, U, and this patch here, V. Okay, and in that particular coordinate patch, the map that I'm taking is from Rm. Okay, more specifically, it's actually not the full Rm, but this maps to a subspace of Rm, which is phi of U. Okay, where phi takes me from U to points in Rm. Okay, an open subset in Rm. So strictly speaking, the domain is phi of mu, and the range is now phi of V. Okay, sorry, not phi, psi of V, where psi are the coordinate functions on N. Okay, we define them with coordinate function psi. So now the map that takes us from this coordinate system to this coordinate system is psi circle F circle phi inverse. Okay, so psi circle F circle phi inverse. Okay, this is a map from Rm to Rn. And the domain is phi of u, and the codomain is psi of v. Okay, so it takes you from phi of u to psi of v. Okay, so it takes us from one coordinate system to another one coordinate system on M, the manifold M, to another coordinate system on the manifold N. Okay, a coordinate patch. So now if we write phi of p, okay, that is the coordinates of p, we just denote them as x mu, okay, as we've been doing before. But x mu, the mu runs from 1 through m. because there are only m coordinates on the manifold capital M. Okay, and on the second manifold, if we take the point f of p, okay, which is the image of the point p, then psi of f of p, okay, gives me the coordinates of that point, okay, which will denote as y alpha, and the values of alpha only run from 1 through n, okay, because this is an n-dimensional manifold, and capital N is assumed to be n-dimensional. Okay, so the coordinates are also n-dimensional. And now if we use these coordinates, okay, then we can write this map psi circle f circle phi inverse. That is nothing but calculating the y coordinate corresponding to a particular x coordinate, okay, under this map f. Okay, so it's basically psi circle f circle phi inverse acting on x. X acted by phi inverse takes me back to the point p. Acted by f takes me to the point f of p, which is now in the manifold n. And now when I act on this with psi, it gives me the coordinates on the manifold n, okay, which is y. Okay, so this is what we're really doing. Okay, we're going from the coordinates x to the coordinates y. These coordinates are on the manifold n. These coordinates are on the manifold m. Okay, and this is the transition function, which strictly takes us from these coordinates to these coordinates. It's not f itself. Okay, you really have to go back to the manifold from the coordinates. And then once you reach the new manifold, you have to again find the coordinates of the point on the new manifold. Okay, so that's why these coordinate functions phi and psi are involved. Now, with a slight abuse of notation, okay, with our understanding of which coordinate system we are using, so assuming that we know which coordinate patch we're talking about, in shorthand, okay, we can write this as y is equal to f of x. Okay, so this is a slight abuse of notation, and you see why it's an abuse of notation, because f is strictly speaking the map between points on M and points on N. Okay, and we are omitting the coordinates that we're using. Okay, but with an understanding that we know which coordinate patch we're talking about. X is on the particular coordinate patch that we're using in M. Y is the particular coordinates that we're using in N. Okay, the fully correct notation is this one. Okay, and so in short, we'll write it like this, or another way of writing it is y alpha, where alpha runs from 1 through n, okay, because again there are n coordinates on the manifold capital N, is equal to some function f of alpha. Okay, again there are n functions. Okay, you can regard these as component functions of this capital F of x mu. Okay, where these are all the x mu's, where mu runs from 1 through m. Okay, because there are m coordinates on capital M. Okay, so it's important that this shorthand notation, okay, you only use this when you know which coordinate systems you are using on M and which coordinate systems you are using on N. Assuming you already understand which coordinate patch you're talking about, then it's perfectly fine to write this. Okay, there's no ambiguity about the shorthand notation, and we will often use this. Okay, when we understand which coordinate system we're referring to. Okay. Now we define the notion of differentiability. Okay, so these functions, these transition functions, which are basically, instead of going from the manifold M to the manifold N, we are going from their coordinates on the manifold M to the coordinates on the manifold N. Okay, and we are defining for each value of mu, okay, we can differentiate this function, these f alphas. Okay, so if for each mu, then we say that f is, so if these functions are C infinity, that is, they can be differentiated infinite number of times, okay, with respect to each of these x mu's, then we say that the function f is, then we say that the function f is differentiable at the point P. Okay, and now what we mean by the function f is not this fake function which actually includes coordinates, but rather we say the original function f between the manifolds is differentiable if this function between the coordinates is differentiable. Okay, is that idea clear? Because we've defined the notion of differentiability only between Rm to Rn, and now what we're saying is that this is taken from some point P. Okay, sorry, this is P and this is the coordinates of P. Okay, And now what we say is that the function f, which is a function between m and n, that is differentiable at p. Okay, that function is differentiable at p. Okay. So this is just a name that we're giving. Okay, we're saying that the function is differentiable if the coordinate functions, the coordinate transformation function is differentiable. Okay, or the coordinate map is differentiable. The map from coordinates in M to the coordinates in N. If those functions are differentiable, then we say that f is differentiable. Okay, so the key point is that now we're extending the notion of differentiability away from just the coordinate representation to the actual map between the manifolds themselves. Okay, and now what we want to understand is this definition, okay, a consistent definition? Can we think of this as differentiation directly on the manifold itself? Okay. Okay. Yeah. So either you say that f is differentiable, or you talk about it in the coordinate representation and say psi circle f circle phi inverse is differentiable. Okay. The coordinate representation, this is easy to define. Okay. But the notion of differentiability on the manifolds, that is the thing that is non-trivial. Okay. Because this relied on a particular coordinate choice. Okay. But as we'll see, because the manifolds, okay, allow smooth transitions between any coordinates that you use on the manifold, okay, this definition of differentiability doesn't really depend on the coordinate system that you use. Okay, it doesn't really depend on the particular coordinate system that you use. Okay, so differentiable maps are also called smooth maps. Okay, so this map between manifolds M to N, if it's differentiable in the sense that we defined it, then we say that this is a smooth map. Okay, and here we only define smoothness at a point. You need to define smoothness over the entire manifold. So at all points P, if f of P is differentiable for all P belonging to M, okay, then you say that this is a smooth map. Okay, this function f is a smooth map. Okay, so the important point which I'll show now is that differentiating f, this notion of differentiability of f, which is the map between the manifolds, is actually independent of the particular coordinate system that you're using. Okay, so suppose, for example, that you take, let's look at this picture. Okay, so let's imagine that you take a manifold M and you take a point P which lies in an overlap region between two coordinate charts, U1 and U2. Okay, so it lies over here. So P belongs to this intersection of, sorry, not phi1 and phi2, U1 and U2. Okay, and U1 and U2 are two open sets in the atlas of M that contain P. Okay, and N is this manifold, and now F is a map which takes us from the point P to f of P. Okay, so this map F obviously doesn't care about which coordinate chart you're using. You can use the coordinate chart U1, you can use the coordinate chart U2, but you're still talking about the same point P. Okay, let's say in the overlap region. Okay, and the same point P under this map F always takes you to this point f of P. So now in one coordinate representation, so I can use the coordinates associated with this patch U2, okay, and that takes me to some Rm, okay, some subspace of Rm, and there's some coordinate which I associate with that. Okay, so let's say under the map phi2. And similarly, I could instead use the coordinates of P under the chart U1, and I would get some coordinates which through the map phi1. Okay, so let's denote these coordinates as x, and let's denote these coordinates as x prime. Okay, so I could have used the x coordinates for this point P. I could have used the x prime coordinates for this point P. Okay, depending on which coordinate system I'm using. Now, the notion of differentiability, okay, is the statement that, so the way we have defined differentiability is, so we started with one coordinate system. Okay, so we chose, let's say, the x coordinate system, and we said that the functions y of x, okay, that is, now we can directly think of the map from this coordinate system x on the manifold M to this coordinate system y on the manifold N. Okay, and this map, okay, which is psi circle f circle phi2 inverse. Okay, that is, we reverse phi2. Okay, this map is C infinity at x. Okay, this was our notion. This gave us a notion of differentiability at the point P. Okay. But is this notion of differentiability the same as the notion of differentiability if we had used this other coordinate system? Okay, that is, if we had defined instead, okay, the map from this coordinates to here, and this would have been denoted as psi circle f circle phi 1 inverse. Okay, and we would have said that the point P is differentiable. This function f is differentiable at P if this function is C infinity. Okay, so the question that we have is, we've defined differentiability using a particular coordinate system. Okay, does the fact that this function is equal to C infinity imply that this function is also C infinity? If it does, then what it means is that the notion of differentiability really has nothing to do with the particular coordinate system that we use. In any coordinate system used to describe this point P, the functions will be C infinity. Okay. In other words, okay, what we're saying is this map, okay, from this coordinate to this coordinate is y of x. Okay. If we had used the other coordinate patch, okay, then we are trying to find the functions y of x prime. Okay, that is, we're transferring from the coordinates x prime on the manifold M. Okay, so instead of describing the same point P by coordinates x, we're describing the same point P on the manifold by coordinates x prime in a different coordinate system. And now we want to ask, is it guaranteed that this is C infinity? Okay, is this C infinity? And the answer is yes, because we are using smooth manifolds. Okay, because on a smooth manifold, we already know that the transition functions from x prime to x, okay, that is, if I want to make a transition from this function to this function, okay, this coordinate to this coordinate in the overlap region, these functions by definition on a manifold are C infinity. Okay, these functions are C infinity. Okay, so in other words, what is this function y of x prime? Okay, instead of thinking about directly going from this coordinate system to this coordinate system, we can smoothly go from this coordinate system to this coordinate system. That is, we're going from coordinates x prime to coordinates x. And now through our map f, okay, we are going from this point x to this point in y. Okay, so y of x prime, instead of going directly from x prime to y, okay, which would be y of x prime, we can imagine that we're just smoothly transitioning, okay, from x prime to x and then from x to y. Okay, in other words, we are calculating y of x prime. Okay, so in other words, since this transition function is smooth, okay, because of the smoothness of the charts, and this transition function is smooth because by definition we assumed that this is infinitely differentiable. Okay, so this composition of these two functions is also infinitely differentiable, or in other words, this y of x prime is also infinitely differentiable at x prime. Okay, so basically the fact that your charts are smooth, okay, ensures that the definition of smoothness of this function f defined through one coordinate system actually carries over to all the coordinate systems. Okay, any coordinate system that you employ on M. Okay, so the notion of differentiability of this function f, which is now between arbitrary manifolds M and N, is actually independent of the coordinate systems that you employ. Okay, the fact that it's differentiable is independent of the coordinate systems that you employ. Okay. Okay, so now let me just give you the formal definition of what I just stated. Okay, so let there be a map f from manifold M to manifold N. Okay, and let this map be a homeomorphism. Okay, then that is, it preserves open sets. Okay, under this transformation. Then f inverse, and this implies that the f inverse function exists by definition of what is a homeomorphism. Okay, that f inverse exists from N to M. And this is also continuous. Okay, so f is some continuous function because it's a homeomorphism, and then the inverse also exists because by definition of a homeomorphism. Now, what we say is that if you have such homeomorphisms, f and f inverse, and these are also differentiable, okay, that is in the notion of differentiability that we've already defined, at all points p belonging to M, and P prime belonging to N. Okay, if there's a homeomorphism between two manifolds M and N, okay, such that these functions which were homeomorphisms are also differentiable, okay, that is they're infinitely differentiable or they're smooth functions, then we say that the map F is not only continuous, but we also say that it's a diffeomorphism. Okay, that's a definition of what we call a diffeomorphism. So a diffeomorphism is a homeomorphism which is also smooth. Okay, that is, there's a notion of differentiability of these Fs. Okay, so sorry, there were two different concepts that I was covering. One is the notion of differentiability. Okay, and the notion of differentiability is independent of the coordinate system that you employ. Okay, and the second thing is that if you have two manifolds which are homeomorphic to each other, but the homeomorphism is also differentiable, okay, then you say that the manifolds are diffeomorphic. Okay, which means that you can think of the transformation from M to N as not only being continuous, but you can think of it as there's a notion of smoothness of this transformation. Okay, so one way to distinguish between, let's say, a diffeomorphism and a homeomorphism, okay, is to imagine that bending that we were talking about. Okay, so if you imagine the topological space of real numbers and another topological space of real numbers, okay, there are several ways in which you can do a mapping from real numbers to real numbers. Okay, so you can do functions like this. Okay, arbitrary functions from y to x. And it's so for example, if you have something like this, y is equal to x, this is a homeomorphism. Okay, this is also diffeomorphism because it's infinitely differentiable. Okay, this kind of function. Okay, and here on the manifold of R, I'm also using the default coordinate patch. Okay, which is I'm mapping R to R. Okay, so the coordinates are just the standard choice of real numbers. So this gives me this is a continuous map, okay, from x to y, and it's also infinitely differentiable. But I could also have a mapping which sort of looks like this, okay, which is let's say sharp. Okay, so I could have a notion that that sort of looks like sorry. This, and then the derivative here is discontinuous. Okay, so something like this. So this is a continuous map, okay, from x to y, but the transition is sharp. So the derivatives, because this function would be something like y is equal to minus x for x less than 0, and is equal to x, let's say 2x, sorry, minus 2x for x greater than or equal to 0. Okay, so this is clearly continuous at x is equal to 0, the value is 0, but the derivative is discontinuous at x is equal to 0. So this is not a diffeomorphism, but it's a homeomorphism. Okay, but we're now defining the notion of diffeomorphisms and homeomorphisms more generally than just between manifolds which are isomorphic to some Rm or Rn. Okay, these are manifolds which are general manifolds. Okay, for example, spheres. Okay, we can define a notion of diffeomorphisms between spheres and so on. Okay, so roughly in the examples that we had done about homeomorphisms, we thought of spheres of any size as let's imagine two-dimensional spheres. Okay, which live in 3 dimensions. Okay, are embedded in 3 dimensions. So this is the surface of this ball, and we can deform one to another. Okay, and this deformation, as long as it's continuous, that is, you preserve, let's say, neighborhoods of points, okay, as you go from one to another. Okay, this deformation, so one way to imagine this is slowly just expand the ball as if you're inflating a balloon. Okay, that is a homeomorphism. Okay, but that is also a diffeomorphism because there's a notion of smoothness, and you can show in a particular coordinate choice that you will get smooth. There's a notion of smoothness, that is, the coordinate transition functions from here to here are infinitely differentiable. But there's another way in which you can deform a two-sphere to a two-sphere. You can imagine pinching this at some point. So you can imagine pinching it so that it becomes infinitely sharp. okay, at some point. Okay, so this is like the notion of a discontinuity in some kind of first derivative. Okay, and you can still do that, and then you can make this pinch, and then you can unpinch it. Okay, and then make it into a bigger sphere. Okay, and that would be a homeomorphism. That is, it would be a continuous map, but it would not be a diffeomorphism. That is, it would be the derivatives would not be defined through that transition. Okay. Okay. So now, for any two manifolds, okay, if M and N are diffeomorphic, okay, we write M is equivalent to N. Okay. Okay, and so the point is all diffeomorphisms, okay, all these these differentiable maps are homeomorphisms, but all homeomorphisms are not diffeomorphisms. Okay, so this kind of pinching, okay, or sort of non-differentiable homeomorphism, okay, those are uh, those are not diffeomorphisms. Okay. Okay. Yeah. Any questions at this point? Yeah, Tosha.
Sir, in one line, you wrote when you showed that y as a like from going to x primed. So
Uh,
before this,
yeah. Yeah.
this line, sir, y as a function of x primed is equal to y, isn't it? Y as a function of x primed as a function of x. I mean, x primed as a function of x.
No, because x prime is the ultimate. So what I'm doing is I am trying to get to y from x prime. Okay, I'm trying to figure out what the y's are from x prime. Now there are two different ways I could do this. I could directly calculate, okay, by going like this, okay, getting to this point, okay, and then transitioning through f and then coming down here. Okay, that's like the direct method. Okay, of going from here to here. The indirect method is because I have these smooth maps, okay, which take me from x prime to x, I can just go from the x prime coordinate to the x coordinate, okay, and then from there to the y coordinate. So I'm still calculating y for a given x prime, but as an intermediate step, I'm calculating the x coordinate associated with the same point, okay, with coordinates x prime, and then I'm calculating the y coordinate, which is the map of this x. Okay, that is, we're calculating y of x, which is basically through equivalent to this function. Okay, um, which is from this coordinate system on M to this coordinate system on N.
Yeah. Okay, sir.
Other questions? Okay, let's keep going. So so now let's consider several manifolds. Okay, so let's imagine that you have several manifolds. All of them have the same topological space, okay, M, but they have different atlases. Okay, so that is, they have different patches, this different patchwork of coordinate charts. Okay, so imagine the same topological space M with an atlas A1, the same topological space M with an atlas A2, and so on. Okay, now uh, now the question is, are these two, okay, manifolds with this the same manifold with so the same topological space, okay, the same topological space with a different atlas, are these diffeomorphic to each other? Okay. Now the claim is that these are all diffeomorphic to each other, okay, if the atlases A1 and A2 are compatible atlases. That is, if I take the union of A1 and A2, if that also gives me an atlas, okay, then and what are A1 and A2? A1 and A2 are basically ways to break up M into coordinate patches. Okay, so you're fixing U's, that is, you're fixing these open subsets, and you're fixing phi's, which are transition functions, from these open subsets to our to n-dimensional real space. Okay, so and now Atlas 1 is something like this, and Atlas 2 is some other covering, okay, with some other map to coordinates. And now the claim is, if I join both of them together, do I still get an atlas? Okay, and we've seen that that is not necessarily true. At least I told you this in the last class. We haven't shown it, but in the last class, it's not necessarily true. For some exotic manifolds, it's not necessarily true. Okay, but if they have the same, if the atlases are compatible, then you would say that MA1 and MA2, or MIAI and MAJ, as we defined in the previous class, we said that they have the same differentiable structure. Okay, they have the same differentiable structure, and so all manifolds within the same differentiable structure. We saw that differentiable structure, having a differentiable structure, is an equivalence class. So all manifolds where the atlases are such that if I take their unions, that also gives me an atlas. They fall into one class of manifolds. Okay, and this gives me a differentiable structure. Okay, this is said to give a differentiable structure, this equivalence class. And although this differentiable structure is not unique, okay, I mean, it's not at all obvious, right? Like we discussed in last class, when I patch these together, okay, the pink atlas and the white atlas, that it still gives me an atlas, because the transition functions between the pink coordinates and the white coordinates, those also need to be smooth. Okay, it seems like it should happen, but it turns out that there are exceptions. Okay, but if you can do this, okay, then they fall in the class of having the same differentiable structure. And in fact, all these manifolds are then diffeomorphic to each other. Okay, all these manifolds are diffeomorphic to each other. Okay, so this differentiable structure, so all these manifolds having, if they're in the same class of having the same differentiable structure, then they are also diffeomorphic to each other. And diffeomorphisms therefore give you an equivalence relation on manifolds, okay, which is the same as the notion of differentiable structure, which is, oops. Yeah, okay. Yeah, so basically we partitioned our manifolds into classes like this. Okay, so MA1, MA2, and so on. Okay, and this is class 1, this is class 2, and all of these are compatible atlases. Okay, and this is some A1 prime, A2 prime, and so on. And these are all compatible, okay, atlases. But any member of this class and this class are not compatible. Okay, all these manifolds are diffeomorphic to each other, which means that you can choose any of these coordinate systems. Okay, and that's a and you can smoothly transition from choosing one coordinate system to switching to another coordinate system. Okay, that is, these manifolds are diffeomorphic to each other. So this idea of splitting things into classes based on their differentiable structure is equivalent to choosing manifolds which are diffeomorphic to each other. Okay. So in fact, we will think of this this kind of class itself as the manifold. Okay. So typically we will think of this kind of class itself as the manifold. That is, we won't associate a manifold with a particular coordinate chart. We will say any of these charts is good enough, okay, for that manifold, because all these manifolds can be smoothly transitioned from one to another through diffeomorphic maps F. Okay, and therefore all of these manifolds are in some sense equivalent manifolds. Okay, it's like taking R4, okay, and making a coordinate rotation, okay, and using different set of coordinates. Okay, you would still think of it as the same space. Okay, so that's what we mean by these are diffeomorphic to each other. They're independent of the coordinate choice that we use. Okay. Okay. Now the set of diffeomorphisms. Okay, the set of all diffeomorphisms. That is, if you take a manifold M and you transform it to the same manifold M. Okay, maybe with a different coordinate chart. This set of diffeomorphisms forms a group. Okay, denoted as diff M. Okay. Okay, you can show that this set of functions F, okay, forms a group. Okay, that is diff M. Okay, so going from a group in the mathematical sense. Okay, so there's an identity group which is just the trivial map from M to M. That is, you take the point P and you map it to the point P. Okay, and then there is you can compose two operations. That is, you can take F circle G, and this gives you a third function H, which is also a map from M to M. Okay, and therefore it's a member of the same group. That is your closure. Okay, and then you have associativity. Okay, so F circle G circle H is equal to F circle G circle H. Okay, so it doesn't matter what order you take these operations. Okay, I mean, you'll still get the same diffeomorphism. Okay, so you can see that these diffeomorphisms form a group, and that group is denoted by diffeomorphisms on the manifold M. Okay, and one way to if you want to be concrete about what you mean by these diffeomorphisms is to specialize to particular coordinates. So if you think about this P and this point as f of P, what you're doing is in a particular coordinate system, you call this the coordinates of this y, and you call the coordinates of this x. Okay, and now the set of diffeomorphisms that you can make is taking arbitrary coordinate transformations from x to some other coordinates y on the same manifold M. Okay, so this such that this yx is C infinity. Okay, and yx is an arbitrary coordinate transformation that is C infinity. Okay, so the set of all such coordinate transformations is what we call an active diffeomorphism. Okay, we think of this as an active diffeomorphism in the sense that it's a map from well, it's actually we're taking two copies of the manifold. We're taking the original manifold and another copy, and we're just writing this as a transition from a point X on this manifold to a point Y on its copy. Okay, so this is the point of view of what we call active diffeomorphisms. Okay, there's another point of view of what we call passive diffeomorphisms. That is, you can think of just the same manifold M, but you can think of many coordinate patches. Okay, many coordinate patches for the same point P. Now, in two different coordinate patches, the same point has coordinates y and coordinates x. Okay, and if you've taken all possible patches, okay, if you've taken all possible patches, then you will get all functions. So in some patch, you will get some function y of x. Okay, and these y of x will be C infinity functions. Okay, and indeed, if you take all possible coordinate systems on this manifold, you will cover all possible functions, all possible coordinates that you can choose. Okay, which are infinitely differentiable. So this is, but in this sense of looking at it, we're looking at the transformations from x coordinates to y coordinates as transformations on the same topological space. Okay, so this is what we call passive diffeomorphisms. That is, we're just changing coordinates. Okay, it's a change of coordinate system. Okay, and this point of view, we're thinking of changing from x on one copy of M to a point y on another copy of M. So this point of view, you're essentially doing the same thing. Okay, but the point of view that's taken here is that these are what are called active diffeomorphisms because of this notion of copies. Okay, the set of transformations that you're making mathematically is still the same. Okay, and here we assume that the manifolds that we're mapping between this M and this M, okay, we're assuming that they have the same atlas. Okay, but they could have different atlases. So if you have different atlases on this manifold and this manifold, okay, then these coordinate transformations are not necessarily arbitrary. Okay, but if I want to take the set of all possible coordinate transformations, then I should consider what is called the maximal atlas. That is, in a particular equivalence class, okay, in this particular equivalence class, I could have assigned coordinates using atlas A1, I could have used coordinates using atlas A2 and so on. And the union of all these atlases is also an atlas, okay? And this might be an infinite set. You take the union of all those atlases, that you take all possible coordinate patch ways to break up M into coordinate patches, okay? And you take all possible coordinates that I can assign to those coordinate patches. And that maximal atlas, okay, is what you define the manifold M to have. Okay, so M carries the maximal atlas. Then it should be true that when I go from some coordinates x to some other coordinates y, I will get in general arbitrary functions y of x as long as they are infinitely differentiable. Okay, and the set of all such arbitrary transformations gives you what are called active diffeomorphisms. Okay, yeah, any questions at this point?
Hello.
Yeah.
Yes. Yeah, sir, you said that the passive and active diffeomorphisms are the same thing, just look at it in a different way. But isn't P and F, aren't P and FP arbitrarily different points? Like if you give me just 2 points in a manifold that are independent of coordinate systems, then P and FP are different. Whereas the X and Y that you define in a passive manifold are the same point. So aren't there different things where you're changing your point itself, and in this you're just changing the coordinate system? So even the mathematically just a transformation, but they're fundamentally different things, right?
They are different things, but okay. Yeah, okay. So yes, to be clear, you're actually making a different operation. Yeah. Sorry, any other comment, Anish?
Yes, sir. If you have a sphere, let's say S2,
Yeah.
you know that you can cover it with two coordinate charts.
Mm-hmm.
And like if you are using that kind of atlas, then obviously there's only one sort of passive transformation which is possible, but I mean, of course, infinitely many possible active transformations.
Yeah, that's why I said you consider the maximal atlas. Okay, so the maximal atlas would be you choose any kind of coordinate system that you want, break it up into as many patches as you want, as long as the transitions between the patches are smooth. Okay, in that case, both of the mathematically the functions that you're choosing y of x are the same type, but I agree with Adyan that these are operationally different things that you're doing. Okay, in one case, you're just changing the coordinates of a point. In the other case, you're actually mathematically, I mean, operationally, you're thinking of it as transforming the point P to another point f of P. So to give you the example on the sphere, okay, an active coordinate transformation, sorry, a passive coordinate transformation would be like, let me define, let's say, a z-axis, an x-axis, and a y-axis, and let me think about, let's say, coordinates theta and phi on the sphere. Okay, of course, this is only valid on a patch. Let's say you can't cover the north pole and the south pole, but let's not worry about that subtlety. Okay, so you take theta and phi coordinates, and now what you can do is you can relabel on the same patch. Instead of choosing theta with respect to the z-axis, you choose theta with respect to the y-axis. Okay, and of course now the patch is different. Okay, but let's take the subset of those two patches. So we'll remove the north pole, south pole on at every point on the x-axis, y-axis, and z-axis, and we'll define that sphere without all those points as our patch. Okay, and we can take a theta phi, okay, with we can take a theta phi with this as the with either the z-axis as the reference, or we can take a theta phi with the y-axis as a reference. This is a coordinate transformation. It's a passive transformation. Okay, it's just a change of coordinates for the same S2. The active point of view is, let me imagine that there is another sphere Okay, and if I want, I can think of it as having the same x, y, z. And now what I do is I imagine that the map from this S2 to this S2 is such that it rotates the sphere so that the z-axis now points along the y-axis, okay, of the sphere. Okay, so operationally the change of coordinates that I get, okay, for this theta phi, okay, will be mathematically similar to the change of coordinates that I got when I looked at this theta phi, okay, and just change the coordinates on the same sphere. The operation of physically rotating it is a diffeomorphism. Okay, you can imagine doing that in a smooth differentiable way. Okay, and that the point of view is that this is an active transformation. Okay, so operationally, I agree that these are different things. Yeah, I mean that's all. But mathematically, all I was saying is that these functions y of x, you can mathematically you're doing the same thing. Okay, which is in the coordinates, okay, you're trying to find all possible functions y of x to characterize the diffeomorphisms.
So in some senses, if you give me a y of x, I can't tell you if it's an active at the diamorphism or a passive.
Yeah, you can't just tell just by this y of x. You have to tell me which operation you do. Okay. But I mean, I could think of it either way. I can think of this y of x as either being due to a passive transformation or due to an active transformation. It doesn't really matter.
Okay, yeah. Got it. Thank you.
Okay. Okay. So the next thing that we'll do is we'll define a notion of a curve on a manifold. Okay, and this will be very important when we try to define vectors on a manifold. Okay, and then we'll also try to define the notion of functions on a manifold. So the first thing we'll do is define curves on a manifold. Okay, so we'll define an open curve on a manifold M. Okay, so we've already defined maps between manifolds M and N. So in this case, what we'll do is we'll define the map to be between an open interval A to B. Okay, this open interval, either you can think of it as a topological space or you can directly think of it as a subspace on the rail line. And we'll map it to some arbitrary manifold M. Okay, so what we're doing is operationally, okay, we have this interval A to B. Okay, and we'll denote a coordinate on this as some coordinate T. Okay. Or you can just directly think of it, instead of putting coordinates on this point, on this subspace, you directly think of it as a subspace of real numbers. Okay, so T is telling me which real number I'm looking at between A and B. Okay, and C is a map now which takes me from this open interval. Okay, sorry, there's no manifold here. I mean, the manifold is just this open line segment. Okay, the C takes me to a point which I'll denote here as P. Okay, and now as I vary T, okay, as I change T, I go from A to B, okay, and I get different points in the manifold M. Okay, so this gives me a curve C of T. Okay, and you can imagine that this is a one-dimensional object. Okay, it's just tracing out a single curve in this manifold, and it's one-dimensional because whatever the C of T is, it's homeomorphic to this interval A to B. Okay, it's homeomorphic to this interval A to B. So you imagine that this C is a smooth function. Okay, that is, it's not only continuous, but it's also differentiable. Okay, now let's look at this in a particular coordinate representation. Okay, so let's take this point P and let's take a coordinate patch. So I've shown this coordinate patch here. In this coordinate patch, this point P has some coordinates in Rn. Okay, using this function phi. So in the coordinate patch, let's assume again you get some kind of curve, okay, in the coordinates, okay, through this n-dimensional coordinate space. Now I can think about the map directly from AB, okay, to this coordinate patch. Okay, so this map could be something like phi circle C. Okay, that is. Where is it? Phi circle C. Yeah, so first I act with C and I go here, and then I go here with phi. Okay, so first I act with C, then I act with phi, And or equivalently, I can think of this as a map directly from this interval AB to the coordinates, okay, over here. Now, this map will not work when I switch my coordinate system. That is, supposing the curve goes outside one particular coordinate patch, then I have to switch to another phi. Okay, I have to switch to another phi. But at least for the part of the curve that is contained within this coordinate patch, I can continue to use this function, phi circle c. Okay. So at least this is valid as long as I stick within this this patch. Okay. So now in a coordinate representation, we can easily represent this curve within the coordinate patch as this phi circle c, because this phi circle c is a map from an open interval on real numbers to some open subset of Rn. Okay. So some open subset of Rn, or in the coordinate representation, it's very simple. You're writing functions x mu of t. Okay. So it's like x0 of t, where t belongs to this open interval AB. Okay, and when I specify all the xn's, okay, and so on, then I'm specifying a unique point in Rn. Okay, and that is telling me where I am for some particular value of t. Okay, so now we say that this curve, okay, this curve on M, this curve on M is smooth. Okay, we say the curve is smooth if x mu of t is infinitely differentiable in all patches that the curve passes through. Okay, because this x mu of t is a well-defined function from real numbers to Rn. So the notion of differentiability is defined. And we can now define a notion of, once we have a notion of differentiability, we can talk about differentiability on of this map C itself. And if the map C is differentiable, then we say that this curve is a smooth curve through M. Okay. And one other assumption that we'll make is that the curve does not intersect with itself. That is, the map always takes you from a unique point here to a unique point here. Okay, you don't get back the same point for two different values in AB, in this interval AB. So we'll assume a non-intersecting curve. Okay, so one t value gives you one point P on the manifold M. Okay, if you want to consider closed curves, then instead of considering a map between this open interval AB to M, you're considering a map from the topological space S1, okay, to M. And as we've seen, the topological space S1 cannot be covered by a single coordinate chart. Okay, so you'll have to use two different coordinate charts. I mean, if I want to represent where I am on this S1, I can't specify it by just a single number theta, okay, in a continuous way. Okay, that's what we've already discussed. So you'll have to use two coordinate charts to define this map from a closed for a closed curve. Okay, so this gives us a notion of curves and a notion of smooth curves on a manifold. Okay, it's quite easy to see. It's just a map from an open interval to the manifold. Now you can define also what are called functions on a manifold. Okay, which is kind of like the reverse of what we've done. So now what we're doing is we're taking points P on a manifold. So the idea of a function is that you're taking maps from the manifold to real numbers. Okay, that is, for every point P on the manifold, I want a function which takes this P as an input and returns to me as an output some number on the rail line. Okay, that's a function of the manifold. So given a point on the manifold, it spits out a real number. So again, I can look at this in a particular coordinate representation. So I can take a particular coordinate patch like this over here, look at phi of P, okay, that gives me some point in Rn. And now if I want to ask in this coordinate representation, what is the function that takes me from here to the point on the real line? So first I operate with phi inverse, go back to the point P, then I operate with phi and with F, and I get to this point over here. So it's phi inverse followed by F. Okay, so F circle phi inverse. Okay, is the operation that I need to do to get from here to here. Okay, and so again, we're assuming that F is a smooth map. Okay, and again, smoothness is defined between arbitrary manifolds, and I can think of this real numbers as themselves being a manifold. Okay, so so this F circle phi inverse, okay, this function, okay, by the smoothness of F is C infinity. Okay, by definition of what we mean by smooth map. So this function is C infinity. Okay, this map from Rn to R, that is from the particular coordinate representation to the real number R. So you can think of this as I return a real number, so this is some f of x mu. Okay, so this is an abusive notation. Strictly speaking, it's f circle phi inverse of x mu. In shorthand, if we know which coordinate patch we're talking about, then we'll just write it as f of x mu. Okay. So this, and if we now take all smooth functions on the manifold, okay, so this gives us a notion of smoothness. And now you take all smooth functions on the manifold. That set of smooth functions is denoted as some curly f of m. Okay, capital curly f of m. Okay, any questions at this point? So we've defined two things. One is curves on a manifold, which are maps from open intervals to m. And we've defined a notion of functions on a manifold, which is maps from a manifold to real numbers. Okay, any questions?
Sir, could you please repeat the point about the closed curve?
Yeah, okay, so for an open curve, so one is we assume that this is non-intersecting. Okay, so by definition, I mean, we assume that this map is such that for every, if a, b, okay, if I have a point t belonging to this a, b, okay, then the point in m, okay, is, so this is a one-to-one function. Okay, which means that for a point in AB, the image is unique. Okay, that is, you don't get back the same point for the same t. Okay, so this will not be a closed curve because you can never, for if I increase t from A to B, I can never come back to the same point. Okay, by the choice of this one-to-one map. Now, for a closed curve, on the other hand, if I want to get a closed curve, I should really define it as a map from a circle to M. Okay, because a map from a circle to M, what it means is, so if I have a map from a circle to this manifold M, it's like I map this. So visually you can understand what I'm doing, right? I take this point and I map it to this point, and the map is continuous. And also it has this additional criteria of differentiability, but let's just look at the continuity for now. So if you look at this point, it's over here and so on. And so you can imagine that you'll trace out something, and then when I come back, okay, because topologically this is a circle, so these points are in the neighborhood of the point that I started with. So eventually I have to come back to the point that I started with. Okay, if this is a continuous and differentiable map C. So this will now give me a closed curve on the manifold. However, if I want to represent this using coordinates, I can't do this using a single coordinate t. Okay, I can't define this as just x mu of t. And the reason I can't just use this as x mu of t is because we've seen already that you can't cover an S1 by a single smooth coordinate patch t. Okay, so you can use a single coordinate patch, but you will have to remove one point, okay, for one coordinate patch. And you can use t as long as you're in that coordinate patch, but coming back to the same point, you can't keep using that same coordinate patch. Right? Because so to use a coordinate patch on this S1, okay, and to represent it by real numbers, t, okay, so I'm representing it by real numbers. So what we saw in the last class, for example, if I try to represent it by a number between 0 to 2 pi, I either have to remove 0 or I have to remove 2 pi. Otherwise it's, sorry, I have to remove some point between 0 and 2 pi, otherwise this is not going to be continuous, okay? So one coordinate choice that we said was, let's remove the point 0. So it's the open interval 0, 2 pi. So we remove this point, okay? But if we want to include this point, one way to do it is to take the coordinate patch, which is like this, where we remove the point at pi. So we take the coordinate patch minus pi to pi. Okay, so in this coordinate patch, if the coordinate is t1, this coordinate patch, the coordinate is t2, then the curve is described in this coordinate patch as x mu of t1. The curve in this coordinate patch is described as x mu of t2. Okay, and the curve, this is an infinitely differentiable function on the coordinate patch where I use t1. This is an infinitely differentiable thing on the coordinate patch where I use t2. Okay, or more precisely, what we were using was theta and theta prime. Okay. But you won't be able to see the fact that this is a closed patch in any one coordinate system. Okay, I mean, you'll sort of see it in the limit, right? As you're coming towards 2 pi, you're getting closer in x mu's to the, so if I take x mu of 0, that is very, 0.0001. This is very close to x mu of 2 pi minus 0.0001, let's say, okay? These x mu's are very close to each other, but I can never quite get to the point x mu 0 in this coordinate patch, okay? But I can get to the point x mu 0 in this coordinate patch. Okay, that is the one that corresponds to this point. Okay, so in at least one coordinate patch, I can see that this curve closes. I just have to switch to the right coordinate patch to see that it closes.
Yes, sir, it's clear.
Okay. Okay, any more questions?
So, sir, when we define functions on a manifold, is it necessary that the codomain must belong to R only? Can't it belong to some higher dimensional subset like R, N?
Yeah, you could generalize this idea. Okay, you can define functions from M to Rn. Here we're just taking the simple functions, okay, the scalar functions, which will just return a single number.
Okay, sir.
Yeah, so you can extend this idea. I mean, this map, right, is effectively, it's a map between manifolds. So the notion of maps between manifolds, we've already defined this notion of differentiable maps. Okay, so Rn is also a manifold. I mean, you can think of it as a manifold and you can assign appropriate charts to it. Right, and it's also covered by a single chart. So that's also important. Yeah. Okay. All right. So now what we'll do is, so I'll just start some of the ideas about vectors. Okay. So now that we have this notion of curves, okay, we'll find that this is actually very helpful if we want to define the idea of vectors on a manifold. Okay. So let me give you first an intuitive idea today of what exactly we mean by a vector on a curved space. Okay. Or some kind of manifold. So if you imagine, let's say, the surface of the Earth, okay, and like we were doing, when we were thinking about curved space a few lectures back, okay, so you imagine that there's some point on the, let's say, the equator, and I want to define the notion of a vector. Okay, so normally when we are in, let's say, Euclidean space, we think of the notion of a vector as, let me start with some point. Okay, this is the tail of the vector, and let me draw some other point, and that's the head of the vector, and this defines a vector for me. Okay. That's one way to think about how to define a vector. Okay, but how did you draw this line? Okay, you drew a straight line from this point to this point. Okay, and now on a manifold, so what is a straight line? A straight line is the line with the shortest possible distance which connects these 2 points. On a manifold, we don't have a notion of distance. Okay, we don't have any notion of distance yet. Okay, the manifold is only something which has coordinates on it, but it doesn't have a notion of distance between any 2 points. Okay, so for example, if I use x and y and you use a different set of coordinates, you might get a different distance. Okay, I mean, you have to define, first of all, we've not even defined a distance measure, okay, between 2 points. When we're thinking of Euclidean space, we're thinking of a distance measure as dx square plus dy square is the distance between xy and x plus dx and y plus dy. So we don't have a notion of distance measure, so we don't know how to draw straight lines between 2 points. That is, if we draw 2 points, first of all, we don't know how to draw a straight line between them. Second, the straight line is in some sense curved, okay, as we go from one point to another point. Okay, so this idea of drawing vectors in an arbitrary manifold, okay, it's not obvious how to do this. Okay, so this notion of straight line definitely fails. Okay, so the straight line connecting two points, that definitely fails. Okay, so we need some other way to define vectors on a general manifold. So the manifold is it doesn't have this notion of a distance measure between any 2 points. Okay. So one other way that you might think that you could define a vector is to use what is called a tangent vector. Okay, that is, if you imagine a sphere. Okay, even if I don't think about the notion of distance, I can imagine sort of constructing a tangent plane, okay, to the sphere at this point. Okay, and I construct this tangent sphere and tangent plane, and then I can define vectors in the plane. Okay, because the plane roughly is Euclidean. Okay, now where did this come from? This came from the fact that this two-dimensional sphere, we thought of it as embedded inside R3. Okay, we thought of this embedding inside R3. But when we think about general manifolds, okay, we don't know if they're embedded inside some higher dimensional manifold or not. And more importantly, we don't want to refer to some particular embedding, because as we've seen, you know, the topological properties of, let's say, these two rings and, you know, these connected two rings, the fact that these are homeomorphic to each other, okay, can be seen in one embedding, but it can't be seen in another embedding. Okay, it looks not obvious if I embed this in R3. Okay, but in R4, it's easy to see that these are topologically equivalent. Okay, so we don't want to rely on any kind of embeddings. Okay, we want a notion of tangent vectors or vectors which in some way doesn't really rely on the fact that this manifold is embedded in some higher dimensional space. Okay, so this notion of tangent vectors or tangent plane relies on an embedding. But we don't want to give up on the idea of tangent vectors, but we just have to find a different way to think about tangent vectors without thinking of embedding. Okay, so we want to think about tangent vectors without an embedding. Okay, so what we'll do is let's take a manifold M. Okay, and we've defined the notion of a curve on this manifold. Okay, so some kind of curve. Okay, so if I take the curve at some point P, okay, we want to think of in some way about the tangent to this curve. Okay, and what we mean by the tangent to this curve at this point. Okay, that's the basic idea of how we'll try to define a tangent vector. Okay, we'll take a curve through a point P. So if we want a tangent vector at a point P, we'll first take a curve through it, some curve C, and we'll try to define a notion of a tangent. Okay, at this point. So, and then what we'll do is we will take all possible curves. Okay, so this curve, and so on. And each of those curves will give us some notion of a tangent or a tangent vector. Okay, so all of these together will give us a tangent vector space. Okay, and this tangent vector space is in some way similar to this tangent plane that we were thinking of. But this tangent plane that we were sort of imagining, okay, was arising from the embedding of this sphere in R3. Okay, but this notion of curves, the curves themselves are defined on the manifold, so they don't rely on an embedding. And we'll see that there's a notion of talking about the tangent of the curve, okay, at each point, in such a way that it doesn't rely on an embedding. Okay, and therefore, this will allow us at every point P on the manifold to define a set of tangent vectors and therefore a tangent vector space, okay, at every point P. So there'll be some notion of what we mean by a tangent or a tangent vectors or a tangent vector space at every point P on the manifold. Okay. The other important point that will be here is that each point P has its own tangent vector space. Okay, so this P prime has its own tangent vector space, this point P has its own tangent vector space, and so on. Okay, so okay, so let's see how to formalize this definition. Okay, so what we want to do is roughly define the tangents for any curve C at the point P. Okay, so we want to define a notion of the tangent line to the curve C. Okay, so let's think about usually how we define the tangent, let's say for 1D functions. Okay, so if we take maps from real numbers to real numbers, okay, one way we define the tangent is you take, let's say, a function from y x to y. Okay, you draw, let's say, a plot of it. Okay, and so this is some kind of curve. Okay, this is some kind of curve in y. You can think of it as a curve in y. And now we're trying to find the tangent at some point x0. Okay, this x0 tells me a specific point in y. This point is y of x0. Okay, and we know that you can construct a Taylor series of this function y of x around the point x0, and so the Taylor series looks like this. So y minus the value, so y in some small neighborhood around x0 looks like y minus y of x0 is equal to some a, where a is the slope of this tangent, times x minus x0. And then of course you will have higher order terms as I move further away from this neighborhood. Okay. But this a is in some sense what we can think of as the slope of this line, okay, or the tangent. Okay, so it gives us some notion of a tangent. Okay, but we have to think about this slope as something associated with y itself. Okay, not associated with x. Okay, because y itself is, so this y is like the manifold and x is like the mapping from AB to this manifold, which gives us a curve in the manifold. Okay, so now this a, which we can write, the value of the slope, okay, is dy by dx in, so it's basically delta y by delta x in the limit that delta y and delta x go to 0. Okay, or in the limit delta x goes to 0, and this is evaluated at a specific point. It's evaluated at the point x is equal to x0. So this is the tangent, or what we call the slope of the curve. Okay, and here of course there's only one direction. Okay, the direction is in the y direction. Okay, and if the slope is positive, then you'd say that the slope, then you can think of it as in some sense an increasing function, and so the direction is, let's say, in the positive y direction. If the slope is negative, then you can think of it as, let's say, in the minus y direction. Okay, but this slope is just a sort of a number. Okay, in this one-dimensional space y. So what we want is some way to generalize this idea of a tangent to now cover an n-dimensional space, or sorry, an arbitrary manifold. Okay, not just real numbers. Not just real numbers. Okay, but we want to use the same idea of derivatives to define the tangent. Okay, the tangent to the curve, or the slope of the curve. Okay, so let's generalize this idea, and we'll formalize this notion of a tangent. Okay, so let's just draw this picture. Okay, so what we'll do is we'll start with a curve C on a manifold. Okay, so this curve C, as we've seen before, is defined by taking an interval from A to B and drawing a map C which goes from this interval to the manifold. So this gives us a curve. And let's take a point P on this manifold, and let's assume that, so this is a curve C of T, and let's assume that the point 0 is contained between this A to B. And let's first, I mean, this 0 is without loss of generality. It doesn't matter what, there's nothing special about 0. It's just a reference point. Okay, so let's take the image of 0 to be this point P. So P is just C of 0. Okay, it's this point corresponds to 0. Okay, P corresponds to point 0 in A to B. And now let's take also from this M. So this is like a manifold. Okay, and this manifold, previously we would think of this manifold as X. Okay, this is some X. Sorry, this is some Y. Sorry. Okay, let me not just try. Let me not try to relate it to the previous example. Okay, so now let's think of a function from this manifold to real numbers. Okay, so we've also seen how to define a notion of a function from this manifold to real numbers. And now we can think of this entire thing as, so now we have a curve, okay, which takes us to points on the manifold, and these points on the manifold can be mapped to real numbers through this function f. Okay, so in other words, f circle C is directly a mapping from the real interval AB, okay, to real numbers. Okay, and we're assuming all of these are smooth functions. Okay, so these are all smooth functions or differentiable functions. Now we can, instead of looking at this map from this open interval AB, okay, to real numbers. Okay, so this is really what we meant by the map from like X to Y, and the differentiability of Y is gives us a notion of a tangent. Okay, so that's what we're going to try to do. Okay, we're going to try to get the notion of a tangent by differentiating this function. Okay, by differentiating this function, or in some sense finding the slope of this function here, okay, we are going to get the notion of a tangent. Okay, and the way to look at this is again to look at a particular coordinate system. So again, we look at a coordinate system, but the results that we get will not depend on the particular coordinate system that we use. Okay, so let's take a particular coordinate system. So let's use some coordinate patch where we use some transition, some coordinate function phi. So that tells us that this point P has coordinates x. Okay, and so again we can define phi circle C as we can think of is the map directly from AB to the coordinate representation of P, that is this x. And we can think of F circle phi inverse, that is phi inverse and then followed by F, as the map from this x to some point in R. Okay, so the coordinate representation of this F circle C, I can think of as, first let me go, instead of going directly from AB to some point in real numbers, or AB through the manifold to real numbers, I can now go to the coordinates of the point P, and from the coordinates of the point P, I can go to the real numbers. Okay, so this transition, okay, you can think of now as so in shorthand, what we'll do is we'll write this as I start with a coordinate t, okay, on this interval AB. That gives me an x of t. Okay, that x mu of t. Okay, that gives me coordinates of the points on this curve. And now from coordinates on the points on this curve, I want real numbers. So that is f of x mu of t. So that takes me to here, which is f of x mu of t. This is just shorthand way of writing it. Okay. So this f is a function of where I am on this curve. Okay, where I am on this curve. Okay, and t parameterizes where I am on the curve. So we have, so what are the ingredients? We had a curve C and we had a function f on the manifold. Okay, so we had a curve C and a function f, and the manifold automatically came equipped with its coordinate charts. So what we are going to do now is we are going to define the tangent vector at C0, that is at this point P. We're going to define the tangent vector to be the directional derivative of this function. Okay, this function f of x mu t or f of ct. Okay, along the curve C of t at t is equal to 0. Okay, in other words, we're going to try to define a derivative at this point of the curve. Okay, and it's going to be a directional derivative. That is, it will be a derivative along the curve itself. Okay, so that will give us a notion of a vector. Okay, so that's let me just do that definition and then we'll stop for today. Okay, so we'll define this notion of this directional derivative. So this f of ct. Okay, so this is, if I think about it directly, this is f of ct. In the coordinate representation, I can think of it like this. Okay, so now what we want to do is we want to define this derivative df by dt of ct at t is equal to 0. Okay, this derivative is going to help us to define the a vector. Okay, and the important point is that this derivative exists independently of the choice of coordinates. Okay, because this is a smooth map. This is a smooth map. So the notion of differentiability exists. Okay, this notion of differentiability of these maps exists independently of the coordinates that you assign to this point P. Okay, so this is a very important property because we want to be able to define vectors which do not rely on coordinates. Okay, or the vector space at P should not rely on the coordinates that we assign to P. So this is we'll see that this allows us to define a vector, and this derivative exists independently of the particular coordinate representation. Okay, however, it's convenient to evaluate this in a particular coordinate representation. So you can evaluate this derivative in the particular coordinate representation. You can think of this as t instead of directly, if I think about ct, c of t is directly taking me to a point on the manifold P. Instead of thinking about the point on the manifold, we can now think of going from C to the coordinate point X, and then from X, sorry. So I just inserted a phi and a phi inverse. Okay, so F circle, phi inverse, circle, phi, circle C. So instead of directly going from T to the point on the manifold to the value of f of P, okay, which is the function on the manifold. Instead, what we do is we make a stop. Okay, so we go from T to the point P, then we find the coordinates of P. Then from the coordinates of P, we go back to the point P, and then we go to f of P. Okay, and so when we do this, in other words, what we're doing is first we're finding the coordinates of that point on the curve. So we're finding x of t, which is this, and then we're finding f of x. What is the function evaluated at that point in the curve? Okay, so in other words, we're finding f of x of t, okay, which is what I had written earlier. Okay, so finally, I'll just write this expression and then we'll stop. Okay, so df by dt. Okay, so we can define the derivative of this f of c of t as df by dt is equal to, and now we can write this as there are n mu x coordinates. So mu is 1 through n, labels the x coordinates. So I can take partial f, partial x mu, okay, dx mu dt. So this is just by the chain rule, okay. So there are n coordinates, okay, at this intermediate stopping point where I find the coordinates. So I can write it as there's an implicit sum here where mu goes from 1 through n. Okay, partial f, partial x mu, dx mu dt. Okay, this notation is somewhat reminiscent of special relativity in the sense that I'm using an upper mu, but every time I write the coordinates, I'm just going to use this. Okay, for now. So there's no concept yet of a lower index. Okay, x upper index mu labels the coordinate on the manifold. Okay, and I evaluate this derivative at t is equal to 0. Okay, so now I have a notion of a derivative. The notion of the derivative exists, okay, independently of the coordinate choice, but in a particular coordinate choice, I can write this in this way. Okay, using those particular coordinates. So in the next class, what we're going to see is how to use this derivative to define vectors. Okay, and more generally a vector space. Okay, so first we'll define vectors at P using this derivative, and then we'll define a vector space at P. Okay, and these vectors are associated, each vector is going to be associated with a particular curve. Okay, the vectors are going to be associated with a particular curve. Okay, any questions here? Otherwise we'll stop. Is the idea clear of taking a curve and finding sort of a notion of a derivative of this curve at this point when I map this curve to a function f? Sorry, when I map this curve through a function f to real numbers. Okay, I mean, if there, I'll just stop the recording. If there are no more questions, we can stop. Otherwise, if